Think about this for a moment. It takes us about 3 days to travel to the Moon, and 7 months to the nearest planet, Mars, 15 months to Venus, 6 years to Jupiter, 7 years to Saturn, 8.5 years to Uranus, 9.5 years to Pluto, the closest dwarf star, and 12 years to Neptune, the farthest planet. You may be thinking why it takes longer to reach Neptune than it does to Pluto. These times were calculated using the technology of the time that we use to send rockets or probes to each prospective planet. So, how large is the universe then? Well, the observable universe is 93 billion light years away from one end to the other. We can't begin to comprehend the mind-blowing size of space. Although you might think the trip to the grocery store is far, it really isn't. It is estimated that the Milky Way Galaxy alone has about 100 billion stars, and that the entire universe has at least 140 billion galaxies. The Royal Albert Hall-sized space would be filled with galaxies if they were frozen peas. So, how was this unimaginable giant created? Let's look into this topic in this video and find out how the universe was formed. The Big Bang is the central idea in the most well-researched theory of the creation of our universe. This theory was developed in response to the observation that galaxies outside of our own are traveling very quickly in every direction, as if they had all been propelled by a powerful explosive force in the distant past. A Belgian priest by the name of Georges Lemaitre first proposed the Big Bang theory in the 1920s, contending that the universe emerged from a solitary primordial atom. Both Arno Penzias and Robert Wilson's discovery of cosmic microwave radiation in the 1960s, which they interpreted as echoes of the Big Bang, and Edwin Hubble's observations that galaxies are speeding away from us in all directions, gave the theory significant boosts. The Big Bang's tempo has become clearer thanks to more research. It goes like this. The universe was extremely small during the first 10 to the power of -43 seconds of its existence, being less than 1,000,000 billion times smaller than a single atom. The four fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, are thought to have been forged into a single force at such an incomprehensibly dense and energetic state. But our current theories haven't yet figured out how a single, unified force would function. We would need to understand how gravity operates at the subatomic level in order to accomplish this, but we don't yet. The very first particles in the universe are thought to have mixed, mingled, and settled into a temperature that was roughly the same thanks to the extremely close proximity. Then, in an incredibly short period of time, all that matter and energy expanded outward roughly evenly, with minute variations being provided by fluctuations on the quantum scale. The inflationary model of the universe's quick expansion may be able to explain the universe's uniform temperature and matter distribution. After inflation, the expansion of the universe slowed considerably. It is still unknown exactly what caused inflation. More varied types of particles started to form as time went on and matter cooled. They eventually condensed into the stars and galaxies of our current universe. The universe had cooled down to the point where the four fundamental forces had separated from one another by the time it had existed for a billionth of a second. The basic elements of the universe were created as well. But because it was still so hot, many of the modern subatomic particles like the proton hadn't yet come together from these individual particles. This boiling primordial soup, known as the quark-gluon plasma, kept cooling as the universe kept growing. Some particle colliders, like the Large Hadron Collider at CERN, have the capability of producing the quark-gluon plasma once again. Radiation in the early universe was so strong that interacting photons could combine to form pairs of matter and antimatter particles. Except for having the opposite electrical charge from matter, antimatter is identical to ordinary matter. It is thought that in the early universe, matter and antimatter were equally distributed. Photons could no longer combine matter and antimatter as the universe cooled. As a result, a large number of matter and antimatter particles paired off and annihilated one another, resembling a very intense game of musical chairs. Somehow, extra material made it through and is now the material that makes up galaxies, planets, and people. We are living proof that matter and antimatter are subject to different laws of nature. This rule imbalance, known as a CP violation, has been experimentally observed in action. How matter prevailed in the early universe is still a mystery to physicists. The remaining matter coalesced into protons and neutrons, the familiar particles that make up the nuclei of atoms, within the first second of the universe because it was cool enough to do so. Additionally, the protons and neutrons had formed the hydrogen and helium nuclei after the first 3 minutes. By mass, hydrogen made up 75% and helium 25% of the matter in the early universe. A major prediction of the Big Bang Theory is the abundance of helium, and this prediction has been supported by empirical data. Atomic nuclei were present in the young universe, but the temperature was still too high for electrons to gather around them and form stable atoms. The universe continued to be a dense electrically charged fog, making it difficult for light to pass through. It would take another 380,000 years or so for the universe to cool down enough for neutral atoms to form, a crucial period known as recombination. The cooler universe was transparent for the first time, letting the rattling photons inside finally pass through unhindered. This primordial afterglow is still present in the universe today as cosmic microwave background radiation. The radiation is comparable to that sent through antennas to transmit TV signals. However, given that it is the oldest radiation ever discovered, it may contain a wealth of information regarding the creation of the universe. The universe didn't contain a single star until roughly 180 million years after the Big Bang. That much time passed before gravity could collect hydrogen clouds and transform them into stars. Numerous physicists believe that the first galaxies and stars were supported by vast clouds of dark matter, which outweighs visible matter by a ratio of more than 5:1. The reionization of neutral atoms, a significant chapter in the history of the universe, began when the first stars in the universe burst into flame. An Australian team reported in February 2018 that they may have found indications of this cosmic dawn. First galaxies emerged 400 million years after the Big Bang. Since then, stars, galaxies, and galaxy clusters have formed and disintegrated, eventually giving rise to our galaxy, the Milky Way, and our cosmological home, the solar system. The universe is already expanding, and to the surprise of astronomers, the rate of expansion is quickening. This acceleration is thought to be caused by dark energy, a force that defies gravity. Although dark energy is still unknown to us, it is estimated to account for 68% of the universe's total matter and energy. Another 27% of matter is dark matter. In essence, the universe is composed of less than 5% of the matter you have ever seen, including your first love and the stars above us. So that's the end of the video. Make sure to like the video, subscribe to our YouTube channel, and press the notification bell so you never miss out on our next videos. Until the next video, take care.